Really lucky to have Athul Paul Jacob today, presenting on his work on learning effective policies for human-centric multi-agent systems. He's a PhD student at MIT, advised by Jacob Andreas, and I think a fair amount of this work was also performed at Meta. Yeah, we're really excited to have you here today, and I guess you can take it away. I'll mute myself.
All right. Thanks again for the invite. Yeah, so today I want to talk about a lot of our recent work on learning effective policies for human-centric multi-agent systems. And before I start, I want to acknowledge all these amazing people, set of collaborators across a number of domains, including NLP, reinforcement learning, game theory, diplomacy experts, and others at FAIR and MIT that all these projects that I'll be talking about today was that I worked on with. So huge thanks to them. So with that, let's get started. So as we all know, over the past few decades, we have seen incredible AI advancements in a number of domains, with several AI systems achieving superhuman level or human level performance. And so there's a growing potential for us to both learn from and potentially collaborate with these algorithms. However, the ways in which many AI systems approach problems are often different from the way humans do. Take the example of a self-driving car at a four-way stop sign. Now, we would like this car to conform to existing human conventions rather than its own self-play solution to the problem. Or consider a self-play agent trained from scratch without human data in a cooperative game involving communication. It would almost certainly not converge to using English as the medium of communication. And so as AI systems become increasingly integrated into our daily lives through self-driving cars and now generative systems like ChatGPT and Bard, it is crucial that we design AI systems such that they're effective at interacting with human users. And so in multi-agent situations, whether they do it implicitly or explicitly, AI agents will therefore need to model and understand how humans behave in order to be effective. And so in this talk, I will talk about some of our recent work on building AI agents that can effectively interact and communicate in human-centric multi-agent systems. So this talk is roughly structured as follows. First, I will talk about how we can build effective human-like agents that can act strategically in multi-agent domains that involve humans by regularizing search and reinforcement learning techniques towards a human imitation learn policy. And then I will talk about how this allowed us to develop the first expert level agent to play the board game No Price Diplomacy. And in the second part of the talk, I will describe our work on building effective agents for multi-agent domains that require them to not only act, but also communicate. I will specifically describe the challenges of improving multi-agent language systems using rewards and how leveraging an intent-based dialogue system allowed us to build Cicero, which is our human-level agent for full press diplomacy. So we want to build AI systems that cooperate and collaborate effectively through actions with humans. And for this, it helps a lot if we can first develop a high-quality model of how expert humans behave. One way to model human behavior is through imitation learning. Now, for example, you can take a bunch of human data and train a neural network policy tau on this. Some recent papers by McElroy Young et al. Do this in chess to produce a human model called Maya, with some very good results. However, there are some shortcomings. This plot here compares the approximate ELO rating of agents in chess. Now, as you might already know, ELO rating is a measure of performance, so the higher the better. Maya Chess is trained using imitation learning on millions of games from human players with ELO ratings between 1900 and 2000. But Maya Chess obtains an ELO rating about 1630, which is almost 320 ELO points lower than the humans it is trained to imitate. This is a significant gap in strength. And so we can also see similar patterns in other games like Go, Diplomacy, and Hanabi, where imitation learning on human data produces agents that are significantly weaker in terms of performance than the agents it is trained to imitate. Now, the strongest agents in many of these games that achieve superhuman performance rely on search and combination of reinforcement learning. Take LC0, for example. It is an open source version of AlphaZero, the successor of AlphaGo, that uses self-play reinforcement learning and inference time search without any human data. Its estimated ELO rating is over 3,200. However, these superhuman agents are also not good model of human behavior. Here we have the plot from the MyHS paper that compares the human action prediction accuracy for LC0 and MyHS. LC0 gets an accuracy of 46% on a held out set of human data. MyHS, on the other hand, is trained on human data and gets an accuracy of 52.9. So MyHS outperforms LC0 in its ability to predict human moves. And so we see that imitation learning of human data outperforms search-based methods that don't rely on human data in predicting human moves. So as a recap, we've seen that human imitation learned policies often perform much worse than human experts in settings that require strategic forward planning. However, search and reinforcement learning methods that do not leverage human data, while they perform as well or even better than humans, but themselves are also poor at modeling humans. So in this first part of the talk, we will look at how we can get the best of both worlds. So consider the space of policies. A subset of this is what we would consider human-like policies. A human imitation learned policy, tau, would live in this space. And another subset is one we would call strong policies. This is where we might find pi star, the optimal policy discovered by a search algorithm or reinforcement learning. We are interested in policies that live in this intersection, that are both strong but also human-like. In our recent work at ICML last year, we show that performing search with KL-regularization anchored towards the human imitation learned policy tau allows us to achieve both strong performance and also model human behavior well, where the strength of this regularization is determined by a parameter lambda. We will first look at how to effectively apply KL regularization to different kinds of search techniques in order to build strong and human-like policies. And later, we will see how we can combine this with self-play reinforcement learning techniques to build effective agents for a strategic multi-agent game. So to reiterate our goal, we want to find policies that are both strong and also human-like. Now, how can we quantify both? We can measure human likeness by measuring the top one accuracy. That is, across a given data set, how often does the policy's predicted most likely action match the actual human action? There are also other ways of measuring human likeness, such as cross entropy. And how can we measure strength? We can do this by measuring the win rate of a particular policy by simulating it against a baseline opponent policy. Again, we also look at other ways of measuring strength, like the performance in a population of players with diverse skill levels. However, at the end of the day, in a multiplayer game like Diplomacy, we are interested in performance against players of diverse skill levels. And so we also do them, and which we will see later in the presentation. Now, before we dive in, a quick recap of notation we will be using in the rest of this presentation. We have S and A that describe the state and actions. Here, A can be a joint action, as we will see later in the talk. Q of SA that describes the expected value of action A in state S. This could be obtained with a deep neural network evaluation or recursively via further search. Then we have tau, which, as I mentioned earlier, is our human anchor policy, which is typically trained using imitation learning. Finally, we have pi which is our final policy that we actually care about. So we'll first look at KL-regularized search in two-player sequential games like chess and Go. So just as a recap, in a two-player sequential game, we start in a state S0, where the first player, pi1, performs an action A1. This transitions the game to S1, where the second player, pi2, performs an action A2. The game then transitions to S2, and the control reverts back to pi1. This continues until the game terminates, where one of the players receives a reward of +1, and the other receives a reward of -1. As I mentioned earlier, chess and Go are popular examples of two-player sequential games. Now, a popular search technique used to find strong policies in this setting is Monte Carlo tree search, or MCTS. And we'll see in a bit how MCTS is surprisingly convenient choice given our goal. At a high level, MCTS operates by incrementally growing a game tree, starting with some node, repeatedly picking some path to explore down the tree, and performing a rollout or deep neural network evaluation, and then walking back up the tree, updating all the value estimates based on that result. As you might already know, MCTS is the core search algorithm and the core technique that was leveraged by the family of AlphaZero-like algorithms. Now, at each node, MCTS treats it as a multi-arm bandit problem, incrementally exploring an action and observing the predicted reward from the subsequent rollout or deep neural network evaluation, and then trying to find the actions that maximize that reward. For our work, we use a fairly standard AlphaZero style exploration for the multi-arm bandit. At each step, we explore the action that balances the competing objectives of searching the moves that have higher Q value estimates versus exploring other possible moves. Now, the exploration term here critically depends on a prior policy, pi0, such as the output of a deep neural network, to predict what moves are a priori more likely to be good, so that the search can be efficient. Along with coefficients and scaling terms that affect the strength of that prior. Notice that if we consider the scaling term fixed, we can tune the parameter CPU-CT to vary the strength of that prior. So if we set the CPU-CT parameter to a very large number, it effectively approximates the prior policy before search. And setting it to 0 is equivalent to performing the greedy argmax of the Q value estimates. Now, recall that we want to find a way to do KL-regularized search given a human anchor policy, and hopefully producing a final search policy that is still very human-like, but which is much stronger at matching human expert performance. So how do we do this for MCTS? Consider this utility function, which is just the expected utility of pi according to the current Q values in the search. And then subtracting a KL divergence penalty for differing too much from the prior policy pi0, and lambda that determines the strength of this regularization. From a paper not too long ago, it turns out MCTS, by exploring the tree in the way we saw earlier, is actually already optimizing this objective. So MCTS is already doing what we need. So we just have to use the human imitation learn policy tau in place of the prior policy pi0, rather than, say, a reinforcement learning policy prior that is used in AlphaZero, for example. One important point to note is that the CPU-CT parameter we saw earlier is roughly proportional to the lambda term. Now, the idea of using a human imitation learn policy as the anchor policy has been done before in a lot of past works, especially pre-AlphaZero. But surprisingly, there isn't any major work before us that thought to ask the question we are asking. That is, how well this works for making a model that models strong humans accurately, rather than one that just plays well. So with that, let us jump into some of our results. We'll first take a look at chess. On the x-axis, we have the top 1 accuracy of predicting human moves on a held-out dataset. While on the y-axis, we have the win rate against the raw imitation learned model, which is the raw imitation model here is Maya, which, as I mentioned earlier, is the current state-of-the-art model in predicting human moves. Now, what would we expect to see here for MCTS? We might imagine that performing MCTS would improve performance, but potentially at some cost in its ability to predict human moves. In green, we had MCTS-based model with different values of the CPU-CT parameter, where we used this raw model as the prior for search. Now, surprisingly, rather than solely trade off between strength and accuracy, most CPU-CT parameter values in the range that we tested increased both, some achieving more than 90% win rate while still improving human prediction. Now, CPU-CT value of 2.0, for example, gets a much higher win rate while having a much better top 1 accuracy. In Go, surprisingly, we have the exact same story.
Sorry, are you taking questions now, or wait till the end?
I can take some questions, yeah.
Are you going to, maybe spoiler alert, are you going to have an explanation for why that happens, or is it just a surprise?
It was actually a surprise. So,
and do you know why, or we still don't know? It's a mystery.
So basically, it effectively, MCTS, search algorithms, effectively prevents the model from making blunders. And I think a lot of imitation learned models are not actually able to plan and even identify when certain blunders happen, which certain humans, especially expert level humans, don't actually make. And so in being able to avoid those blunders, this MCTS based algorithm is able to do better than an imitation learning agent.
Let me probe that a little bit. So one consequence of that would be that this phenomenon is a specific choice of using MCTS and not generic to this idea of trying to regularize away from the human policy towards a stronger policy. But on the other hand, I mean, stronger policies in general have to make many fewer blunders. So, I'm not sure I think it's specific MCTS. Anyways, really interesting.
Yeah, no, yeah, happy to talk more in detail about this towards the end. Yeah, and so as I just mentioned, in Go, we actually have almost this exact same story. As in chess, we have a human imitation learn policy. And just like before, adding search to this policy not only increases the win rate, but also improves the human action prediction accuracy. Now, it looks almost identical, but the scale is different. So, but in either way, KL-regularized search effectively allows us to build stronger and more human-like agents in both chess and Go. Now, I'll talk about another class of...
I have one more question.
Yes.
Can you go back?
Yeah.
I guess I note that the x-axis here is actually a pretty highly compressed range. I mean, you're all kind of within 1%.
Right.
So even like the one that's regularized all the way up to like 0.5, or I'd be curious about 0.1, like the performance is way better, but actually the difference from a human doesn't seem that, like, is that even detectable? Like in practice, like, is that really a difference that even matters along the x-axis?
So the prediction accuracy, so what we actually care about, as I mentioned earlier, is the fact that, when you do imitation learning, we're actually able to get match per move prediction accuracies pretty well already. But the moment you deploy that against actual human players, you see that the issue that we have is mostly in terms of strength. And so it's actually really good, even if you can get the same prediction accuracy but just improve the performance. Then we are more likely to match how a strong human player would play. But that said, we haven't actually deployed these agents in an online setting. So we haven't been able to estimate the ELO ratings, for example, for these agents. But that's something that would be definitely relevant. We do these kinds of experiments for the next section, where we talk about diplomacy. All right. Yeah, so I'll talk about another class of games called simultaneous action games. Notationally, we are going to consider single stage, 2 players, zero-sum simultaneous action games. And I'll define what those are. We will then see later how we can apply to a complex multi-stage 7-player game called diplomacy. So what does this look like? We start in a state S. We have 2 players, pi1 and pi2. The players pi1 and pi2 then simultaneously perform actions R and C. Then they each receive a reward, Q1 and Q2, such that the sum of rewards is 0. Typically, simultaneous action games are often described with a payoff matrix. Now let us look at a concrete example, which many of you might already have seen before, even Prisoner's Dilemma, for example. But just as a recap, we have pi1 representing the rows, who can play 2 actions, R1 or R2, and pi2 representing the columns, who can play C1 or C2. The entries in the matrix describe the rewards received by the players. For example, if the row player plays R2 and the column player plays C1, the row player receives a reward of -1 and the column player receives a reward of +1. More formally, let us define U of I of pi1 and pi2 to be the expected utility obtained by player I when player 1 plays pi1 and player 2 plays pi2. Now, what would be an optimal solution in such games? A popular optimal solution concept for games in 2-player zero-sum simultaneous action games is called Nash equilibrium. Recall that a Nash equilibrium is joint policies for both players such that neither player is incentivized to unilaterally deviate by playing a different policy. An algorithm for finding Nash equilibrium in 2-player zero-sum games is called hedge. Now, we won't go into the details of this algorithm, but informally, hedge is an iterative algorithm that maintains the cumulative utility or value of each action for each player so far. And at each iteration, players sample actions according to this following equation, where the probability of playing each action is proportional to the exponential of the cumulative utility of that action on all previous iterations of the algorithm, with eta being a parameter that depends on that iteration. And at the end, the average strategy of players produced by hedge is known to converge to a Nash equilibrium. Unlike in MCTS, hedge does not already do a form of KL-regularization. And so we have to introduce something new here. We call this new technique policy regularized hedge, or PICO. To be more concrete, suppose we have a human imitation learn anchor policy. We wish to regularize the utilities we saw earlier towards. We can add our desired KL regularization to hedge. Recall from MCTS, we simply had a KL term in the utility being optimized. So exactly analogously, we can add a KL term to the utility for hedge. Now, this is the same thing as in MCTS, except for a bit of additional notations reflecting that we have 2 players acting simultaneously. Note also that the direction of KL loss between the policy and anchor is reversed. And we do this because it turns out to make the implementation and theoretical analysis simpler for hedge. In practice, you can do it either way and get reasonable results. Analogously, our per iteration policy needs to be adjusted to be consistent and sound given the new definition of utility. Now, this was the policy we had at an iteration T. We can update this to the following. Our new policy is updated not just based on the cumulative utility of an action, but something proportional to the log of our action policy, anchor policy tau. Again, we don't go into the detail here, but notice as lambda tends to 0, this is just regular hedge. But as lambda tends to infinity, this converges to playing the anchor policy tau. In our ICMO paper, we show that the average policy produced by pickle hedge stays close to the anchor policy, and that the average policies for the players produced by pickle hedge converges to a Nash equilibrium under the original non-regularized utilities. Again, we skip over a lot of the details, and so we invite you to take a look at that paper. And with that, we can now evaluate how pickle hedge compares experimentally with other approaches. Now, we do this in the no-press variant of the 7-player simultaneous action game called Diplomacy, which many of you might already be familiar with, which has large combinatorial action space, where doing well requires both adversarial competition and cooperative coordination with other players. Many of you might already be familiar with the rules, but I'll do a quick overview of the game. The goal is to control the majority of the map on the game board. The game is set in Europe, with each of the 7 players controlling one of the 7 powers. Players negotiate alliances, support each other through private one-on-one conversation. Now, there are no binding agreements, and so players can often misrepresent their plans and even double deal. The objective is for a single player to control the majority of the 34 supply centers on the map. One of them is indicated on the screen here. You do this by using one of 2 different types of units, armies or fleets. Now, each player starts with 3 or 4 centers. The number of units you own corresponds to the number of centers you hold. So if you lose a center, you have to remove a unit. Or if you gain a center, you're allowed to build a new unit. And then after natural language negotiations, players write down their moves, which are then executed simultaneously. Crucially, the only way to win is by building trust, negotiating, and then cooperating with other players. At a high level, diplomacy therefore has 2 main components: a strategic reasoning component that has to identify the moves to make on the board, and a dialogue modeling component that determines what to say and to whom. As I described earlier, a popular variant of the game is called no-press diplomacy, which does not permit explicit communication between players. However, implicit communication through moves on the board is still permitted, which we will see later. Now, what are the specific characteristics to do well in no-press diplomacy? It requires the agent to be able to outplay an opponent in 1v1 situations, the ability to effectively coordinate, signal intents, and even seem human, and the ability to determine when to change alliances. All these aspects makes no-press diplomacy a great domain to study strategic multi-agent reasoning in a human-centric multi-agent system. In our work, we model the game as a repeated simultaneous action game. Suppose we are in a particular phase of the game, which is state S. Now we can consider all possible joint actions for the 7 players, but that is just not tractable, as there are combinatorially many such joint actions. And so in our work, we first consider a proposal policy that filters the most promising joint action candidates. Now we can use the game engine to find the states that each of the joint action transitions the game to. Finally, we can evaluate the new state using a Q-value function. So now with the proposal policies and the value function, we get a 7-dimensional payoff grid similar to what we saw earlier. And we can then leverage equilibrium search algorithms to find strong policies. As a recap,
I have a
yes.
very naive question. I mean, does a game like No Press Diplomacy have a Nash equilibrium at all?
Yeah. So if you consider each stage of a game, yes. And in general, these games do have Nash equilibrium, but we kind of, when we run these algorithms, we don't actually find the Nash equilibrium.
Right, of course, it's intractable, but it's interesting the game even has one. I wouldn't have known that for sure. So
yeah,
cool. Thanks.
Yeah. So Hedge takes in a human imitation learned proposal policy and an imitation learned value function that are learned from a human play data set to find strong policies for each player. And Pickle Hedge leverages the same policies and value function, but also takes in a lambda parameter and imitation learned anchor policy. For Pickle Hedge, the proposal policies and anchor policies are generally the same. And with that detour out of the way, let us look at some of our results. Now, similar to what we saw in chess and Go, we consider a similar plot. On the x-axis, we measure the top one accuracy of predicting a human action. And on the y-axis, we show the average score obtained by the method when facing off against 6 copies of a raw imitation learned policy. First, we have the unregularized search methods, Hedge and regret matching. Regret matching is just another iterative algorithm for finding the Nash equilibrium in two-player zero-sum games. They get a reasonably high score of 47%. The human imitation learned policy, on the other hand, gets a much higher prediction accuracy, but a lot lower score. In green, we have Pickle Hedge with different values of the lambda parameter, which is the regularization parameter. Notice how by tuning this lambda, you can obtain better performance and human action prediction accuracy compared to unregularized search. And with lambda equal to 1e-1, you can obtain a policy that has much higher performance while also maintaining the human action prediction score. With Pickle Hedge, one can therefore produce agents in no-press diplomacy that are not only strong, but also significantly more human-like. Now, as you can see on the screen, different values of lambda, we observe different behavior for Pickle Hedge on the Pareto curve. In practice, not every player will have the same regularization parameter. Some might play more optimally, while others might play more human-like. And so in our upcoming paper at iClear, we introduce a simple extension of Pickle called DILPickle that replaces Pickle's single fixed regularization parameter lambda with a probability distribution over the lambda regularization parameters. This allows us to be robust to a population of different behaviors. So previously, we defined the utility and policy at iteration t for Pickle as follows. With DILPickle, at each iteration, we sample a lambda parameter for each player from a belief distribution and update the equations as follows. The only difference here being the fact that lambda is no longer fixed for all players, and it can therefore change at each iteration for each player. Now notice if lambda 1 is equal to lambda 2, this is just a Pickle iteration. And as lambda 1 and lambda 2 both tend to 0, that is just a regular Hedge iteration. And when they both tend to infinity, this converges to playing the anchor policy. Finally, it turns out that as lambda 1 tends to 0 and lambda 2 converges to infinity, player 1's policies effectively converges to playing the best response to the anchor policy. Recall the best response policy is one that produces the most favorable outcome for player 1, assuming that player 2 always plays the anchor policy. Again, we have a lot of nice theoretical results in our paper that I won't cover here, but we can show that DILPickle can indeed produce strong policies. Earlier, we saw that for no-press diplomacy, Pickle Hedge leveraged a human imitation learn anchor policy and a single parameter lambda for all powers. With Dill Pickle, our search algorithm now takes in a belief distribution for each power instead. But we still learn the proposal policies and the value function from the human play dataset. Can we do better? Can we leverage self-play reinforcement learning to learn better proposal policies and value functions? The answer is yes. Just like with AlphaZero, we can learn better policies and value functions by using a 7-player self-play reinforcement learning. But as I mentioned earlier, MCTS is unsound in simultaneous action games. And so we instead use Dill Pickle. We call this reinforced Dill Pickle. So the way it works, we start with an initial imitation learn policy and value function trained using from the human data. And during RL training, we compute an improved policy using Dill Pickle. Using this improved policy, we improve our Q value estimates using an algorithm similar to traditional Q learning called deep Nash value iteration, which was introduced in the previous work. Finally, we update our proposal policy, and we do this in a self-play RL fashion. This leads us to our no-press diplomacy agent that we call Diplodocus. It learns the policy proposal and value function using reinforced Dill Pickle and uses the human imitation learned anchor policies from the human play dataset. And during inference and gameplay time, it just uses Dill Pickle using the policy proposal function, value function, and anchor policies that we saw earlier. We compare Diplodocus against a plethora of past no-press diplomacy agents. We evaluate each of these agents in this graph against a population of strong, diverse, human-like agents. You can find the details of that in our paper. The baseline agents here include reinforcement learning-based, imitation learning-based, and search-based agents. Diplodocus significantly outperforms all past agents. And so, earlier last year, we entered Diplodocus variants in an anonymous human tournament that featured over 60 participants that included players of various different skill levels, including experts. Every game featured one of our agents and 6 human participants. Diplodocus was able to successfully outperform all human participants based on average score or the ELO rating. Again, you can find all of those details in our paper.
Can I ask a quick logistical question?
Yes.
So do the humans know they're sometimes playing against a computer? Is that like it's like you work with the organizers of the tournament, or how does that, or you did organize the tournament, or how does it work?
Yeah, so during the tournament, the players knew that they were playing against one bot, but they didn't know which of them it was. Yeah.
And you had to work with the organizers of the tournament to set that up?
We Meta organized it effectively through a third-party agency so that it's fair.
And logistically, do you have a human just entering the computer's moves? Is that, or do you?
Or we just plugged. We had plugged in the API access to the server, so it's just.
Thank you.
Yeah. In our paper, we also had human experts evaluate Diplodocus's play, and they generally consider Diplodocus to be playing at an expert level. Now, of particular interest for NLP researchers would be the fact that Diplodocus does a good job of communicating its strategic intents or its cooperative intents to other players. Here, Diplodocus is playing Italy in green. Now, it wants Austria to think of it, to not think of it as a threat. So at this particular phase in the game, Italy builds fleet units instead of army units in order to signal to Austria that it does not intend to pose any kind of threat to them. So Italy continued to project several other allying signals to Austria. In the game, the expert player who was playing Austria had no idea that Italy was a bot. And so thinking it was a human player, Austria decided not to defend itself against Italy. And in the end, that was actually their fall. A bot sees and the opportunity later in the game to attack Austria. This is another game where Diplodocus is playing as Germany in brown. It is stuck in a long, extended, complicated battle with England in pink. And at this particular phase in the game, the bot had a few options that it could with the fleet unit. It could move the unit to other locations that would allow it to defend against other powers and potentially bolster its position in the north. However, Germany instead takes the drastic action of disbanding its own fleet unit and playing a unit down in order to signal to England that it wants to cooperate. The bot decided that it wanted to send the strongest possible message to England about wanting to ally. And after this action, England sees this and decides to work together with Germany against France in blue. And in every game, there are numerous such human-like signaling behaviors that Diplodocus uses to actually ally with other players. And this was one of the reasons it was able to beat other players. So far, we showed that by leveraging search and reinforcement learning that are regularized towards a human imitation learn policy, we can build effective agents for human-centric multi-agent systems. And we looked at how we can build strong human-like agents that can act strategically. Now, in the second part of the talk, I'll briefly describe our work on building effective agents for multi-agent domains that require them to not only act, but also communicate. I will specifically describe the challenges of improving multi-agent language systems using rewards and how leveraging an intent-based dialogue system allowed us to achieve human-level performance in the game Diplomacy. We'll look at this, the full game of Diplomacy, which not only requires a strategic reasoning component, but also that we saw earlier, but also requires building trust and negotiating and cooperating with other players through natural language dialogue. Now, how would we build such an agent for Diplomacy? Like before, we could start with a bunch of human data and train an imitation learning agent that is conditioned on the both state and dialogue history to first predict the policies of that agent. And we can then simultaneously train an imitation learning agent to predict the dialogue for the agent. But like before, imitation learning alone cannot match the performance of strong human players. And a dialogue model trained with imitation learning can easily be exploited. For example, a player could tell the agent, "I'm glad we agreed that you will move your unit out of Paris." And since similar messages appear in the training data, only when an agreement was reached, the agent might indeed move its unit out of Paris, even if doing so is a clear strategic blunder. You can actually see this kind of behavior in as people try to jailbreak current chat systems. This is fundamentally a problem of imitation learning. And we have already seen how we can improve strategic policies using variants of Pickle. But how might we improve the dialogue model? We could potentially do something similar to what we did before, perhaps some form of self-play reinforcement learning. But unlike the strategic action space, the natural language action space are incredibly challenging. They're huge and language generation is incredibly slow. There's also a very complex credit assignment problem. And even if those problems weren't challenging enough, you have the problem of language drift. So language drift is the phenomena where models use messages in ways that are inconsistent with their natural language meanings. This happens because during self-play reinforcement learning, fine-tuning, agents will learn to co-adapt and develop new meanings. And even though there are several approaches to tackle this problem, including some of our past work, in a game like Diplomacy, language drift can be a huge problem. If an agent mismaps the specific semantic meaning of a unit's move, for example, it can have a big negative impact in its gameplay as it is playing with humans. And humans will then easily identify it as a bot, which can lead to poor performance. And so in diplomacy, we instead use a form of intent-controlled dialogue generation. What does this mean? And what does this look like? We first train an intent model to predict actions for a pair of players on the basis of their dialogue and board state history. Then we use this model to annotate each message in the dialogue training set with an agreement message injected at the end. We can then train a dialogue model to predict each dataset message given the annotated intent of the target message. So in doing so, the dialogue model we just trained is controllable by a set of strategic intents. In our ablation experiments, we evaluate the quality of dialogue, and we show that intent grounding significantly improves the dialogue quality and across a lot of different categories. Now, with this intent condition model, we can do something interesting. We just saw earlier that using a pickle-based planning agent, we can produce better policies. So during inference, with the dialogue history and board state, you can use a pickle-based planning algorithm to generate better intents. And we can condition this dialogue model on this better set of strategic intents to produce better dialogue. So this intent conditioned dialogue model allows for minimal intervention on the imitation learning policy. And so we don't have to worry about language drift. It also improves the quality of dialogue model since we are effectively offloading the responsibility of calculating the legal moves to the game engine. And finally, this allows for precise control of the dialogue model with a strong planning engine. Now let us look at our intent model in action. So if the intent is that France helps England move out of Belgium, this leads England to generate a message suggesting that move. On the other hand, if the intent is that England supports France's move to Belgium, this leads England to generate a message that asks France if they need England's help. This pickle-based planner that we saw in the first part of the talk, together with the intent condition dialogue model, as well as a bunch of other things that I haven't even touched upon, form the pieces of our human-level diplomacy AI called Cicero. Now, how do all of these things that we talked so far fit together? Yes.
Can I ask a quick question? I know we're getting close to the end, but
Yeah.
If the human responds to your intent and plan, and it's like, no, I will not support you in that, how does that get fed back into the system? Does it?
Yes. I'll be talking about that right now.
Great. Okay, I'll mute myself again. Thanks.
Yeah. So how does this all work together? We first feed the board state and the dialogue so far to a dialogue conditional action model similar to the intent model we saw earlier. This then produces a set of anchor policies for all of the agents, which is then fed into a pickle-based planning module. This is actually quite different from the pickle and dill pickle we saw earlier, but I'm not going to go into the detail here. This module now produces a strong set of strategic intents for the dialogue that the dialogue model is conditioned on in order to produce the output messages. So now to answer your question, each time Cicero gets a new message from any player, it reruns this whole pipeline. in every particular phase. Each time a new player sends a message, this whole pipeline reruns. But when the phase ends, it plays the intent that it had at that particular point in time. Now, as I mentioned earlier, I've skipped over a lot of different additional components that make up Cicero, such as the new variants of Pickle and a suite of dialog filters that were all super crucial. And I suggest that you take a look at our paper if you haven't already to learn more about them. Now, as many of you might already know, we entered Cicero into an anonymous online diplomacy league where it achieved more than double the average score of the human players and ranked in the top 10% of the players who played more than one game. And when players were informed about the game, they were quite surprised to hear that they had played against an AI. Over the course of 72 hours of gameplay that involved sending over 5,200 messages, it was not identified as an AI. And this actually surprised us as well.
Again, in this case, the participants weren't primed that there might be an AI, or they did know or they didn't know.
So unlike the previous tournament, in this tournament, they were not. We did not tell them that they were playing against an AI. So we just entered it anonymously into a league, and because this, unlike the previous tournament, if we had actually told that it's an AI, they were more likely to probe it, and it wouldn't have worked out well for the way that we are evaluating this agent. And
did you tell the organizers, or you didn't tell them either?
No, I mean, one of the organizers that we did work together with did know, but in general, we only told them after the tournament we finished our evaluation. Yeah, so to wrap up, in this talk, we asked the question of how we might be able to learn effective policies for human-centric multi-agent systems. In the first part of the talk, we looked at how we can build effective human-like agents that can act strategically in multi-agent domains by regularizing search and reinforcement learning towards a human imitation learn policy. And in the second part of the talk, we showed how leveraging an intent-based dialogue model allowed us to produce dialogue that is strong and human-like. Together, this allowed us to build Cicero, our human-level diplomacy agent. And again, I want to take a time to acknowledge and thank all these amazing people without whom these projects would not have been successful. And special thanks to Jacob Andreas, Noam Brown, Adam Lehrer, Mike Lewis, and Emily Dinnan for being amazing advisors and mentors across all of these projects. Thank you for listening. I'm happy to take any questions if there
are. Thank you for the amazing talk. As you well know, I'm obsessed with this research. It's really excellent. I guess we have time for maybe one question before folks need to sign off. So if somebody just wants to unmute and go for it. All right, well, so if no last question, I want to go back slightly to the pickle stuff. I'm curious for your intuition about, where is the improvement in predictive accuracy coming from? Whereas I think the previous question answered, where's the strength of the policy coming from? Yeah, I'm curious for your intuition about the predictive accuracy.
Yeah, so unlike in chess and Go, where we saw this nice little behavior where we're able to increase both the human prediction accuracy and the performance, in Pickle, we don't actually see that. We see a typical Pareto behavior where, increasing it's essentially you have to have a trade-off. But if you consider, if you just look at zone in on whether we can build a more match the same performance while also preventing blunders, that effectively gets you that boost in performance. And that's effectively what happens when you do heavy regularization. You effectively kind of filter out all the blunder behavior by the agent, and so it's able to do better in terms of performance, but then also maintain the human action prediction accuracy.
Great, thank you so much. And so I'm going to stop the recording now, but thanks so much for this talk.
Yeah.